Thank you very much. I hope you are seeing the screen. So I'm going to talk about some differential linear cryptanalysis results of ours on Ascon. So actually some of these results are already published and some are going to be published soon. So we are supported by some of the projects in this case. So I want to start by thanking them first. So let's start with the famous saying, in theory and practice are the same, but in practice they are not. So this happens actually a lot in cryptanalysis because nowadays we always obtain results theoretically and sometimes we don't check them, mostly because we don't have the computational power or the storage, because most of the attacks we provide sometimes requires 2 to the 100 or 2 to the 200 encryptions and so on. But actually, they might not work in practice because some of the time we are overlooking some of the properties. We also, for example, we showed in a case where we named a property like differential factors, where in most of the block cipher cryptanalysis, you try to capture the round keys just before the S-box operation, where there's a round key addition. And we realized that sometimes you cannot capture the correct key because some wrong key might always give you the same counter when you perform a differential attack. Another scenario is that sometimes these theoretical attacks may require more data, time, and memory than expected in practice. This is because we are sometimes underestimating some stuff, and this by more, if it is more than like the exhaustive search and so on, this would also mean that these attacks may not work in practice. But sometimes we might be lucky, and these theoretical attacks actually may require less data, time, or memory than expected. And actually, this talk is about this part, luckily. I will give some examples about differential linear cryptanalysis, but the main takeaway from this talk is that toy versions of the distinguishers or the attacks must be experimentally verified because there might be a lot of things that we are overlooking. Okay, so we know that Ascon won the competition, so I'm not going to go much in detail, but I just wanted to mention that in the Caesar competition, initially the initial version supported 96 bits of secret key, but then the designers removed it. In the last slides, I will talk about the exhaustive search attack, so I will briefly mention. So this is why I wanted to mention it now. And also, I want to mention another algorithm called drag Ascon, because I'm also going to give a few results at the end. So just recall that this was also another candidate in the competition, but was eliminated in the second round. Okay, so it uses Ascon, but uses a slightly different permutation. All right. So let's move on to Ascon. So Ascon actually has an internal state of 320 bits. But important thing for us is that in the initialization phase, the first row is actually, so there are 5 rows and 64 columns. At the initialization, the first row is reserved for IV. The second and the third row is for the secret key, and third and the fourth rows are for the nonce, if you're using the main version of Ascon. So there's a round constant addition, which is not important for us. Then we have parallel implementation of 64 5x5 S-box operation. So this S-box is chosen in a very nice way. That's I mean, this is not the best S-box in terms of security, but in terms of trade-off between security and performance, it is very carefully chosen. And we are going to actually try to exploit this S-box. Then we have the linear diffusion layer, where a row is actually added to itself by rotating itself. So here the S-box is on the columns, and this diffusion layer is on the rows. So, and this is the picture from the designers. Thanks for the designers, because they provided a lot of their resources in their webpage throughout this competition process. So we are focusing on this initialization part, but of course, our differential linear distinguishers work for the permutation itself, so you can use it at any place. But if you are focusing here, you can also, you may also turn your distinguishers into attacks. So In terms of attacks, as you can see, we have in the initialization phase, we have IV, secret key, and nonce. And here we are going to introduce differences to nonce. And at the encryption phase, we introduce 64-bit plain text and obtain 64-bit ciphertext, which is the top row of the internal state. So these are the parts that we can obtain. So our actually linear approximation output masks will be on the 64 bits. So this will be more clear in the following slides. All right. So for those who do not work on cryptanalysis, let me briefly explain what a differential linear cryptanalysis is about. So let's start with differential cryptanalysis. Differential cryptanalysis introduces an input difference, and after R1 rounds of encryption, we aim to observe some output difference with probability P. In differential cryptanalysis, we expect this to be a lot larger than from a random permutation. And linear cryptanalysis uses an R2 round linear approximation where XOR of the mask input and output bits are equal to 0 with probability 1 over 2 plus Q. So Q is the bias. So these variables are important for us. So in differential linear cryptanalysis, we combine these two distinguishers. This way we obtain R1 plus R2 round distinguisher. So new ciphers and new designs are resistant against differential and linear cryptanalysis, but sometimes we can combine both of them and obtain longer distinguishers or attacks on larger amount of rounds. But we cannot simply combine a differential with a linear approximation. So assume that at the top we have a differential and at the bottom we have a linear approximation. We can combine them as follows. A differential can be combined with a linear approximation where input mask bits of the linear approximation coincide with the output difference bits that have fixed difference. So I will briefly show them in the pictures. But if you do it this way, in theory, the bias of a differential linear distinguisher is approximately 2 times P times Q squared. And this actually leads to a data complexity with a big O notation, P to the minus 2 and Q to the power minus 4 chosen plain text. So our experiments actually will be on this number. So this is the theory, and in practice, these numbers might be less. So before moving on to results on Ascon, I want to give an older example because this theorem versus practice was actually observed in Serpent. So from a paper from 2008, Dunkerman investigator and Keller actually obtained a very nice 9-round differential linear distinguisher. So in theory, 4 rounds of this distinguisher had a theoretical bias of 2 to the minus 16, and this 4 rounds actually coincides to the last 3 rounds of the differential and the first round of the linear approximation. So they wanted to see how this differential actually matches with the linear approximation. So in theory, it was 2 to the minus 16, but they observed that output of one S-box bit actually has no difference, and I named this after years later of this paper as undisturbed bits. So they reduced it to 2 to the minus 15, but then they performed experiments and they wanted to see what does this bias in practice, and they observed that it's actually less than larger than the theory. So actually, the distinguisher is better in practice than in theory. So in the paper, they say 13.75 here, but since it is from 2008, they didn't have a lot of GPUs or GPUs like this, but they have slower CPUs at the time. So I'm guessing that this correction by me is correct because I performed the test with more data, because nowadays we have GPUs which can perform parallel operations in a very fast way. So they observed that they actually have a gain in practice. So question is, what would happen if we perform this experiment on more rounds? So assume that if we added one more round to the bottom, so this means that 5 rounds differential linear, with first 3 rounds are differential and the last 2 rounds are linear approximation. So the authors didn't do it because in 2008, it will require a lot of CPU power. But again, since we have a lot of GPUs, we performed this experiment and observed that this gain actually increased. So it is, better than expected. So because some people, thought that maybe this gain will be removed, or it will be the same, but it turns out that marginally it is better if we perform experiments on the 5th round. So I continued this way and obtained on the 6th round. So as you can see, the bias is increased now, so you need to perform the experiment on many data, but still marginally we observed that in practice this actually this distinguisher has better bias. So this means that in practice you can perform the attack with less data. This means that you can perform this with less time, or less encryptions. So as you can see, when you combine two different type of distinguishers, in practice it might be better, and sometimes it might be worse. So this is why my main takeaway was that you should experimentally verify toy versions of your distinguishers. So with this knowledge, let's move on to Ascon. So Ascon S-box has some properties. For instance, if you provide this input difference, you would observe that although we might not know output difference on these 3 bits, so I represent it as question marks. This means that it can be 0 or 1, depending on the input. But we know that this bit can have no difference when the input has this difference. So by using these properties, we can easily obtain better differentials, because in the literature, the designers and other people actually try to come up with a good 2-round differential characteristic, but instead by using these undisturbed bits, we actually obtain differentials which has probability 1. So in this picture, you see a probability 1 two-round differential. So we only give difference to this column. As you can see, this bit is not affected due to undisturbed bits, so we have less question marks after the permutation. But then we have this substitution layer again, the permutation layer, so we have a lot of zeros. So now our aim is to put a linear approximation here where the input mask of the bits should correspond to these zeros. So thanks again for the designers that they have a very nice paper about a heuristic tool. So that tool actually can give you nice linear characteristics. So here the notation is changed. So these actually 5 values are just represent 5 rows, and these hexadecimal values are represent the bits where we have masks. So as you can see, actually they are giving a single, they are actually measuring the mask in a single S-box here. So 1 round ago it corresponds to these bits, but in 1 round later it is only affecting the first row of the internal state, because recall that in the encryption part we can only observe this value. So this is why we have no masks on this remaining 4 rows, but we are focusing on here. So if you combine these two, all you need to check if these mask bits actually corresponding to zeros or ones, but not question marks in this picture. So we observe that this actually works. You can check by yourself, but the thing is that since this linear approximation had a bias of 2 to the minus 8, and you combine these two, but this has probability 1, so we get rid of the value p, but we have q as 2 to the minus 8. So in theory, this 4-round differential linear distinguisher has actually a bias of 2 to the minus 15. But the thing is that if you check it in practice, perform experiments, it is really high. As you can see, there's a very huge gap between here, 2 to the minus 2. And this is actually not observed by me, but it was observed by the designers. So people try to, see why this happens. Baran et al. Actually introduced a new concept called differential linear connectivity tables, and they actually said that this bias is actually 2 to the minus 15. In short, what they did was to get rid of the differentials or paths, which doesn't actually affect the mask bits. But still, there is a gap between this value and this. So, in my honest opinion, I think that this gap is due to the multiple distinguishers, because we are trying to measure the bias or the probability of a single distinguisher, but there may be other distinguishers with the same input difference, and the same output masks. So one reason is this, and another reason is the slow diffusion and confusion. Since we are focusing on a very small amount of runs of Ascon, and Ascon is a lightweight design, so we cannot expect it to act like a random permutation in just 1 or 2 runs. So the diffusion and confusion is really slow, so this is why in practice we have higher bias. So before moving on to Ascon results, let me also show what happened with dry Ascon. So the font is really small, but I will explain it in briefly. So we found 2-round differential and then added 3-round linear approximation, and observe that this has bias as like 2 to the minus 8 in practice, so we can distinguish it with this many data. But we said that since the theory and practical bias is really there's a huge gap between them, and there are many different distinguishers, we wanted to check them all one by one, because instead of giving the difference to this S-box, for instance, we can give it to the next S-box. So this would affect as the, changing the places of these question marks, but most probably it will still be, coinciding with this linear approximation, right? So we wanted to check all of them. And at the end, we observed that we actually find a better one as a bias, as you can see, as 2 to the minus 5 compared to this. But the problem is that actually here the mask bits are corresponding to question marks. So this is not something I can obtain in theory, but in practice, if you just give this input difference and look at this output mask, it works with this bias. So this actually shows that since there's a gap between theory and practice, cryptanalysis aim is generally, just finding the best distinguisher in theory. Then we are looking how it works in practice. But here, since we have the computational power, we just wanted to check what happens if we activate only a single S-box. So this way we can obtain better distinguishers, which we cannot obtain in a theoretical way, because I cannot remove some of these question marks. But still, in practice, it gives me the best distinguisher. So this happened in our conference paper at Egypt this February. So we said that in the extended version of our paper, we said that let's do the same for Ascon. Let's perform experiments, try to activate only single S-box, and then try to observe what are the biases. So with this input difference, recall that this first bit is corresponding to first row, which is IV. These are for keys, and these are for nodes. So we are actually giving difference to nodes, and we observe these 4 biases. So you might ask why there are 4 different biases. So we are actually trying to turn it into an attack. So although there are no difference in the key, in practice, the key can take 4 different values for these 2 bits, right? It can be 0, 0, 0, 1, 1, 0, and 1, 1. So we perform the experiments for every possible key combinations, and we observe that, for instance, if the secret key bits here are 1, 1, you have a better bias, and you can actually detect it with less data. Then we said that if the what happens if the attacker has also control over the IV? So in practice, actually, we cannot, but let's assume that we have. So we observed that we can obtain better biases for these 2 key values like 1, 0, 1, and 1, 0. Then we also, I'm about to finish it in a minute. So I observed that we also can give the difference to keys. So this actually gives a lot better bias. So this means that we can have related key attacks with a really nice bias. So since we have very high biases for 5-round, this also gives the idea that maybe we can find 6-round distinguishers. So far we haven't discovered, but we are still using our GPU, so maybe in the future we can show you some 6-round distinguishers. So let me finish it in this slide. So we can use GPUs to obtain fast encryption, but we can also use it to perform brute force attacks on short keys. So our GPU optimizations for Ascon actually achieves 2 to the 35 key trials per second on a RTX 4090 GPU. And to verify these theoretical results, we observed that in a single second, we can actually check 2 to the 35 5-round differential linear distinguishers. So we are checking pairs. So actually, we can verify many theoretical results in practice. So you can play with our optimizations. If you're interested, you can actually come up with better distinguishers if you use these CUDA codes, which are publicly available. You can also obtain the same results that we obtained, that I showed in the previous slides. Thank you for your attention. If you have any questions, I will be happy to answer them.
Thank you, Dion Gibbs. The title of next talk is A Closer Look at the S-box, Deeper Analysis of Round-Reduced Ascon Hash. It will be given by Xiaorui Yu.